Welcome to the deep dive. You've probably heard the buzz about quantum computers.
Oh, yeah, definitely.
They promise to solve problems that are just, well, impossible for even the biggest supercomputers we have today.
Right, revolutionary stuff.
It sounds amazing, maybe even a bit like science fiction, but what are they, really? And, if you start looking into it, you quickly realize there isn't just one kind. People are building them in, like, wildly different ways.
That's the fascinating part right now, isn't it? There's incredible potential, but getting there is this huge scientific and engineering challenge.
Right.
So for this deep dive, we've gone straight to the source. We've got insights from the experts and companies actually building these machines to try and understand the different paths they're taking.
Okay, so our mission today is really to cut through some of the hype
Yeah.
and give you a clearer picture of the quantum computing landscape today. Why so many approaches? What are their unique quirks? What do they all have in common?
Sort of a guide.
Exactly. Think of this as your guide to navigating this really diverse field and understanding why all these different efforts matter.
And to do that, I think we have to start with the absolute basics.
Okay.
The fundamental building blocks and the crucial physics that make quantum computing so powerful and yet, so incredibly difficult.
Right. Let's unpack this. We know classical computers use bits. They're either is 0 or 1. Simple. What's the quantum equivalent?
That would be the qubit or quantum bit.
Quit it.
Yeah. And unlike a classical bit, a qubit can exist in a state of 0, 1, or, and this is where the quantum mechanics comes in, a combination of both at the same time.
That's superposition.
That's superposition. And this ability is really key to their power, but, and it's a big but, it comes with a major catch.
Which is?
These states are incredibly fragile, really delicate.
Fragile how? What makes them lose that special quantum state?
Okay, so this gets us to a really core concept called quantum coherence.
Coherence, okay.
Yeah. It's the ability of the quantum system, so the qubits, to maintain that delicate superposition or another quantum property called entanglement. But the environment, everything around it, is constantly trying to interfere.
Like noise.
Exactly. Thermal noise, electromagnetic fields, even tiny vibrations, stray light, air molecules bumping into things. All of it can disrupt the system.
And make it lose its quantumness.
Precisely.
Yeah.
That process is called decoherence.
So that's why you always hear about these systems needing extreme isolation.
Yeah.
Like super low temperatures or these ultra-high vacuum chambers.
Precisely. Maintaining coherence is the constant battle, and coherence time is a key metric here.
Where does that measure?
It tells you how long a system can actually hold on to its quantum state before the environment inevitably wins and decoherence happens. You only have that limited window to perform your computation.
I heard one expert use a great analogy for this, like a fragile flower in a hurricane.
Oh, I like that.
Coherence is how long that flower can keep its petals intact before the storm, the environmental noise, rips them off.
That's a vivid way to picture it, yeah. You have this incredibly delicate structure, this quantum state, and you're trying to work with it before the outside world just destroys its form.
Got it. So, okay, once you have these fragile, coherent qubits, how do you actually do calculations with them?
Right, that's where quantum gates come in. These are the basic operations.
Like classical logic gates, NED, not T, that sort of thing.
Similar in concept, yeah. They're the fundamental building blocks you use to manipulate the qubits and build your quantum algorithms. You string together a sequence of these gates to run your program.
And I assume, just like with classical circuits, the quality and speed of those operations are critical.
Absolutely crucial. Two major factors here are gate speed and fidelity.
Okay, speed first.
Gate speed is simply how fast you can apply a gate operation. This matters because you're literally racing against that limited coherence time we just talked about.
Right. Faster gates mean more operations before decoherence.
Exactly. You can fit more steps of your calculation into that short window.
And fidelity. What's that?
Fidelity is how correctly the operation is performed. Because these systems are so sensitive, getting a gate to do exactly what you want perfectly every single time is incredibly challenging.
So high fidelity means fewer errors.
Right. It means performing the operation correctly a very large fraction of the time, getting it right much, much more often than you get it wrong. If your fidelity is too low, errors just pile up way too quickly, and your final answer is basically garbage.
So if coherence is the lifespan of our quantum flower, gate speed is maybe how quickly you can, feed it a bee, And fidelity is how beautiful and perfect the flower itself is despite the storm.
Yeah, that works. It's about performing quick, accurate interactions with your very delicate quantum system before it loses its quantum nature, before it decoheres.
Okay, so we've got these fundamental building blocks, qubits,
Yeah.
and these core challenges:
Right.
maintaining coherence, achieving high gate speed, and ensuring high fidelity. And because building something this sensitive and this powerful is so incredibly difficult, it kind of makes sense that nobody agrees on the one perfect way to do it yet.
Exactly right.
Which brings us to the incredible variety we see in quantum computing today. All
Wow.
these different approaches.
Exactly. This diversity isn't just random, it's different teams tackling these same fundamental problems. How to create stable qubits, how to keep them coherent, how to apply high-fidelity gates, how to scale up, but using completely different physical systems.
And each system has its own pros and cons.
Totally. Its own unique set of advantages and disadvantages. And it's highly unlikely, I think most people agree, that one single modality will entirely win.
Ah, so maybe different types for different jobs.
Could be. Different types might be better suited for different problems or applications, or they might even, work together in future hybrid systems. That diversity is actually a strength right now.
Okay, let's dive into some of the major contenders then. Let's start with perhaps the most widely known: superconducting quantum computers.
Right. These are probably the ones people have seen pictures of, those big chandelier-like structures. They use synthetic qubits.
Not natural atoms.
No, these are engineered. They're made from circuits, usually metals like aluminum or niobium, that are supercooled to extremely low temperatures.
Why supercooled?
Well, superconducting means zero electrical resistance, so you avoid energy loss from resistance within the circuit itself.
Okay, so where do they shine? What are their strengths?
They generally offer pretty high gate speeds, which is good, and they've made huge strides in fidelity recently. A major potential advantage, though, is that they can leverage standard semiconductor manufacturing processes.
Like the ones used to make regular computer chips.
Exactly, things like lithography. This means they could potentially tap into decades of existing industry experience and infrastructure, which could really help with manufacturing scalability down the line.
Makes sense. And the downsides? What are the challenges for superconducting?
Their primary challenge historically has been relatively short coherence times compared to some other approaches.
The flower dies quickly.
Kind of, yeah. And they also require this extremely low cryogenic temperatures. We're talking millikelvin, colder than deep space. That's complex and expensive to maintain.
Anything else?
Well, controlling them involves very precise microwave pulses, and some aspects of those microwave interconnects and controlling many qubits at once are still active areas of research and engineering.
But we are seeing significant progress here, you mentioned.
Absolutely. Recent breakthroughs have pushed their 2-qubit gate fidelities up dramatically. Some are reaching 99 to 99.5% fidelity now,
Wow.
which is getting comparable to systems based on, say, pure atoms, which was traditionally seen as an advantage for atom-based systems. Lots of players here, too, the big names like IBM, Google, Amazon, but also companies like Rigetti, Seek, QCI.
Okay, so superconducting, fast gates, improving fidelity, potential manufacturing advantage, but needs extreme cold and has shorter coherence. How do trapped ion quantum computers compare?
Trapped ion systems take a very different approach. They use natural qubits.
Actual atoms.
Ions, specifically. So atoms that have gained or lost an electron, giving them a net electrical charge.
And the advantage there?
Nature makes all ions of a specific element perfectly identical. No manufacturing defects. Plus, because they're charged, you can hold them very precisely in place using electromagnetic fields in a vacuum chamber. That's the trap.
And how do you compute with them?
You use lasers. Precisely aimed lasers are used to cool the ions down and then to manipulate their internal quantum states, performing the gate operations.
Okay, what are the pros of this approach?
Trapped ions are known for having very high gate fidelities. And crucially, very long coherence times.
Longer than superconducting.
Often significantly longer, yes. Another potential big plus is that they don't typically require those extreme cryogenic temperatures. They can potentially operate closer to room temperature, maybe in standard server rack-based systems.
That sounds much more practical.
It could be. And because they use light lasers for control, they could potentially be networked together using standard fiber optics, leveraging, existing telecommunications infrastructure. They currently boast the best average 2-qubit gate fidelities in the field.
Which means less need for error correction.
Potentially, yes. Fewer physical qubits needed to make one reliable logical qubit.
That sounds really promising. So what are the challenges for trapped ions?
Well, there's often a trade-off. The longer coherence times sometimes come with slower gate operations compared to superconducting.
Ah, slower gates.
Yeah, manipulating a system that holds its state for a long time can sometimes take longer. Their main scaling challenge, though, is precisely addressing and controlling a very large number of individual ions with all those lasers.
Getting the lasers to hit the right atom out of thousands or millions.
Exactly. It's a huge engineering feat. Imagine the optics required.
These were some of the first approaches explored, weren't they?
Yes, trapped ion systems were among the pioneers. David Wineland and Serge Haroche won the Nobel Prize for work related to controlling ions back in 2012, and the foundational experiments go back to the 90s. Key players today include companies like IonQ and Quantinuum.
Okay, so we're already seeing a fundamental trade-off shaping up. Superconducting excels at speed, but struggles with coherence length and needs extreme cold. Trapped ions offer longer coherence and top fidelity, but are slower and face different scaling hurdles with lasers.
That's the core of the diversity, exactly. Different physical systems naturally lead to different strengths and weaknesses in tackling those fundamental challenges.
What about neutral atom quantum computers? They also use atoms, but as the name suggests, electrically neutral ones.
Correct. These use atoms that have no net electric charge.
What's the advantage of that?
Because they're neutral, they don't repel each other electrostatically. This means you can potentially pack them much more tightly together than charged ions.
Interesting. How do they work?
Like trapped ions, they are often held in place and manipulated by lasers, typically in optical tweezer arrays. But a key difference is how they get the atoms to interact for gates. They often use lasers to excite the atoms into a special, highly energetic state called the Rydberg state.
The Rydberg state. What's that?
Okay, so normally, an atom's electron orbits pretty close to the nucleus. A laser can zap that electron and boost it into a much higher energy level, making it orbit much, much further away.
But the atom is still neutral.
Still neutral overall, yes. The electron is still bound to the nucleus. But because the positive nucleus and the distant negative electron are now so far apart, the atom develops a large electric dipole moment. It acts like a little bar magnet, but electric.
And that allows them to interact.
Exactly. These large dipoles allow atoms in the Rydberg state to interact very strongly with nearby atoms that are also in that state. That's how you can create entanglement and perform two-qubit gates. They can also use analog control signals, which is a bit different.
Okay, what are the upsides of this neutral atom approach?
Yes, yeah. Well, again, using natural atoms means perfect consistency. No manufacturing defects, just like ions. They benefit from potentially very strong connectivity because you can pack many atoms densely. They also boast long coherence times.
Flexibility, too, I read.
Yes, that's a big point people make. They can potentially operate at room temperature, although often in a vacuum. This opens possibilities for maybe even field deployable systems someday. Plus, the underlying atom technology, manipulating atoms with lasers, can also be used for building highly precise atomic clocks and quantum sensors.
So other applications beyond computing.
Right, which offers potential alternative revenue streams and opportunities for learning and development that can feed back into the computing side. It's a way to maybe monetize the tech earlier.
Makes sense. And the challenges for neutral atoms.
They typically require an ultra-high vacuum environment to operate, which adds cost and complexity. And similar to trapped ions, scaling involves figuring out how to precisely apply and control lasers for a very large number of individual atoms. Getting light to all those atoms in a dense array is tough. Players here include companies like Atom Computing, Inflection, and Pascal.
Okay, so that's three approaches using either synthetic circuits or atoms in different ways, each with its own distinct profile. What about using light itself? Photonic quantum computers.
Yes, this is another fundamentally different route. These aim to use single photons, individual particles of light, as the qubits.
How do you compute with photons? They don't exactly sit still.
Right. The computational model is often different, too. It's frequently based on something called measurement-based quantum computation, or MBQC.
How did that work?
Instead of applying a sequence of gates directly to your qubits, the idea is you first prepare a large, highly entangled quantum state involving many photons, sometimes called a cluster state. Then you perform a sequence of measurements on individual photons within this state. The outcomes of these measurements, and how you choose the next measurement based on previous outcomes, effectively performs the computation.
That sounds intricate. What's the big attraction of using photons? Why go this route?
The immense potential for scaling is the primary driver, I think. It's
Right.
relatively easy to generate millions, even billions of photons. That sounds very tempting compared to the difficulty of fabricating or trapping millions of physical qubits in other modalities,
Not
right?
rolling.
They can also potentially leverage the huge existing silicon photonics industry. Trillions have been invested there. The physics is incredibly well understood, and manufacturing processes are mature.
For things like fiber optics and data centers.
Exactly. Plus, photons are inherently pretty well isolated. They don't interact strongly with the environment, so they can maintain their quantum state over long distances relatively easily. Easier to keep coherent in some ways.
Okay, so what makes them difficult then? What's the catch?
The flip side of not interacting easily with the environment is that it's also very hard to get photons to interact with each other.
Ah, and you need interaction for gates.
Precisely. Getting two photons to influence each other reliably is crucial for creating two-qubit gates and entanglement, which are necessary for universal quantum computation. That interaction is the major hurdle. Generating the initial large-scale, high-quality, entangled state needed for MBQC is also very challenging.
But the hope is, if they crack that.
The hope, or the dream, is that if these fundamental interaction and entanglement problems are solved, the scaling could be explosive. You might be able to go from a limited number of useful qubits to potentially millions relatively quickly because making the photons themselves isn't the hard part.
Who are the major players pushing this photonic approach?
PsiQuantum is a key company really focused on this path. Their strategy is explicitly aimed at building very large-scale, universal, and importantly, fault-tolerant machines right from the start. They're leveraging that silicon photonics technology developed for data centers, and they're talking about moving towards a server rack design, away from those, chandelier-like cryostats.
Okay, fascinating. What about silicon spin quantum dots? That sounds like it's leveraging silicon again.
It is. These use the intrinsic angular momentum or spin of individual electrons as the qubit. And these electrons are confined within tiny semiconductor structures, quantum dots, specifically fabricated in silicon.
So using the workhorse material of classical computing.
Exactly. And that's the major potential advantage they're banking on. The ability to leverage the existing highly advanced and massively scaled up silicon manufacturing ecosystem. The dream is mass production using familiar industrial techniques.
Like superconducting, but maybe even more integrated with standard processes.
Potentially, yeah. They also show promise for strong gate fidelities and pretty good gate speeds. And there's already an existing industry around quantum dots for other applications, like displays and sensors, which could provide a manufacturing head start.
What are the drawbacks currently holding them back?
Like superconducting systems, they typically require very low cryogenic temperatures for operation. They're also still grappling with challenges like interference and crosstalk between neighboring qubits, one qubit affecting another unintentionally. And researchers are still working on developing and demonstrating a full set of reliable, high-fidelity, entangled gates needed for complex algorithms.
But active development is happening.
Oh, yes. There are important academic groups and companies pushing this technology forward, really believing that the silicon manufacturing advantage will ultimately be the key to large-scale quantum computing.
And finally, let's touch on perhaps the most exotic-sounding approach, topological qubits.
Yes, this approach is definitely based on more theoretical, some would say exotic physics. It's famously championed by Microsoft.
How does it work? It sounds different.
The core idea is really clever. Instead of encoding the quantum information in a single, localized physical property, like the spin of an electron or the state of a circuit, you encode it in a non-local way. The information is kind of spread out, encoded in the collective properties or the topology of a specially designed physical system, like their Mayana chip.
Non-local. What's the benefit of that?
The promise is built-in protection. Because the information isn't stored in one specific place, it's thought to be inherently more resilient to local disturbances or noise from the environment. A small local error wouldn't necessarily destroy the encoded information.
Wow, so built-in air protection almost.
That's the big theoretical hope, yes. That inherent resilience to noise is the major potential advantage. This approach also potentially simplifies control. It might allow for more digital-like control signals rather than requiring the extremely precise analog control needed in many other modalities.
And the cons. Why isn't everyone doing this if it sounds so good?
Well, it's described as exotic physics for a reason. Actually, creating, verifying, and controlling the specific quantum states needed these things, called Majorana zero modes, for instance, has been incredibly challenging experimentally. Proving they exist and behave as predicted has taken years.
So it's seen as more of a longer-term play.
Generally, yes. Often seen as a higher risk but potentially higher reward approach compared to some of the others that are based on more established physics. Microsoft did recently announce a significant milestone, claiming they created these topological qubits and shared more data, which indicates important progress, but it's still widely considered a longer journey to get to large scalable systems using this method.
Wow, okay, so let's recap the zoo here. We've got superconducting, trapped ion, neutral atom, photonic, silicon spin, and topological. That's 6 fundamentally different ways people are trying to build a functional quantum processor. You can really see the diversity here.
Absolutely. And it's amazing, isn't it? While their physical implementations are drastically different, from tiny cooled circuits to individual atoms held by lasers to particles of light itself, they all face some common fundamental hurdles.
Like maintaining that delicate quantum state we talked about right at the start. Coherence.
Exactly. The inherent fragility of quantum states, that limited coherence time, is a universal challenge no matter what your qubit is made of. And it leads directly to this core engineering paradox.
The isolation versus control problem.
Precisely. You need to isolate the system perfectly from the environment to maintain coherence for as long as possible, but you also need to be able to interact with it perfectly, control it precisely to perform computations and read out the results. Balancing that isolation and control is incredibly difficult for everyone.
And even with the best isolation and control, errors still happen constantly, right?
Oh, constantly. Quantum systems are just incredibly prone to errors from residual noise or imperfect control. This makes quantum error correction absolutely critical, maybe the critical area for building useful large-scale machines.
What does that involve?
It involves using complex algorithms and, crucially, a lot of extra physical qubits to encode the information redundantly. The idea is to detect and correct errors faster than they occur, protecting the logical information.
Are some approaches trying to build error detection in?
Yes, some are. Like QCI's work with what they call dual-rail qubits, trying to bake some error detection directly into the hardware design itself. That could be very powerful if it works well.
I remember the sources mentioning Google's demonstration of error correction working in principle.
Yes, that was a big deal. Google showed that by applying error correction codes and using more physical qubits, they could actually reduce the overall error rate of the resulting logical qubit. They operated below the surface code threshold, proving the concept works.
And that ratio of physical to logical qubits is improving.
It seems to be. It was once thought you might need, 10,000 physical qubits to make one good logical qubit. Now, with better qubits and improved codes, people are talking about maybe closer to 100 physical qubits per logical qubit for some platforms. That's still a lot, but it makes the path to useful machines seem much more achievable.
Okay, and scalability itself. Just getting enough qubits, that seems like a massive shared challenge across all these different types.
It absolutely is. Getting to the hundreds, thousands, and eventually millions of high-quality, interconnected qubits needed for the really impactful problems is hard, period.
And as we've seen, each modality has its own specific scaling headache, right?
Exactly. Superconducting needs complex fabrication for many layers of circuits and wiring. Atoms need those intricate laser delivery systems. Photons need that efficient interaction and entanglement generation. Silicon spin needs to overcome crosstalk and thermal issues. Topological needs to perfect the fundamental physics and fabrication. Everyone has their mountain to climb.
The goal is often described as building quantum computers on a chip.
Yes, integrating the core quantum components and maybe even some of the classical control electronics onto a single chip or package is seen as key for scaling efficiently. And we need scaling rates that are much faster than Moore's law.
Not just doubling every couple of years.
No, we need factors of 10 increase in capability or qubit count or quality in relatively short periods to get where we need to go. This is why leveraging existing large-scale industries like semiconductor manufacturing for superconducting or silicon spin or silicon photonics for the photonic approach is seen as such a potential game changer for some of these modalities. It offers a path, maybe.
Beyond the physics and engineering challenges, are there other common bottlenecks holding the field back?
Absolutely. A major one that comes up repeatedly is the workforce. There's a significant lack of a sufficiently large pool of highly technical people.
People who can actually design, build, program, and run these things.
Exactly. It requires deep cross-disciplinary expertise, and the talent pipeline isn't big enough yet to meet the growing demand. People are exploring whether AI and large language models could help, maybe by assisting with programming or supplementing developer knowledge to try and alleviate this bottleneck.
On the flip side, investment seems strong, you said. People are putting money into this.
Yeah, big time. There's significant global commitment. Governments worldwide have pledged over $50 billion into quantum technologies. Venture capital is flowing in, and public investors are clearly bullish too. Some quantum company stocks have seen significant rallies. There's a lot of belief in the long-term potential.
And across all these diverse approaches, despite the challenges, the rate of progress feels like it's picking up speed.
It definitely seems to be accelerating. We're seeing important milestones being hit across the board much more frequently now.
Like,
Well, you see things like D-Wave showing useful computation on their annealers that would take classical computers ages. Rigetti hitting those high fidelities in superconducting. Microsoft's topological qubit announcement generating buzz. PsiQuantum breaking ground on large manufacturing sites. And perhaps most importantly, those significant demonstrations of logical qubits improving rapidly, going from maybe 4 to 12 to 28 logical qubits, demonstrated in less than a year by some groups. That's fast progress.
so, despite all these challenges and the, frankly, bewildering variety of methods, real tangible progress is being made, which leads us back to the big question. What are these machines actually for? Why do we really need them when we have incredibly powerful classical supercomputers?
That's the core why, isn't it? The reason is that certain types of problems seem to be fundamentally exponentially harder for classical computers. As the problem size grows, the time or resources needed just explodes beyond feasibility.
What kinds of problems?
Things like precisely simulating the behavior of molecules and materials at the quantum level, which is essential for drug discovery and material science. Tackling huge optimization problems like logistics or financial modeling, where you have vast numbers of possibilities.
Yeah.
And potentially finding new shortcuts or approaches in machine learning and AI.
So quantum computers are kind of built for complexity.
That's a good way to put it. They operate using the principles of quantum mechanics, the same principles that govern that complexity at the atomic scale, so they're naturally suited to modeling those kinds of systems far more efficiently than a classical computer ever could. Trying to simulate quantum mechanics on a classical computer is just incredibly inefficient.
But just to be clear, they're not going to replace my laptop for writing emails or running spreadsheets, right?
No, absolutely not. And this is a critical point for managing expectations. Quantum computers are not going to replace classical computers for everyday tasks. They're seen as complementary.
Like a specialized tool.
Exactly. Think of them as specialized quantum processing units, or maybe even scientific instruments tools designed to work alongside classical CPUs and GPUs within larger computational workflows. They'll tackle the specific parts of a problem that are classically intractable.
So the term quantum computer can sometimes be a bit misleading.
It can be. Thinking of them as powerful accelerators or coprocessors for very specific complex calculations might be a more accurate mental model for most people.
What are some of the early application areas that people are most excited about or actively exploring now?
A major one is definitely pushing the frontiers of basic scientific discovery in physics, chemistry, material science. Using these early machines to model complex quantum systems, particularly systems that are far from equilibrium, which are very hard to study classically.
So understanding the universe better.
Fundamentally, yes. Even if the immediate goal isn't a commercial product, using these machines to learn new things about nature is a key early use case.
And more applied science, like designing new materials or drugs.
Absolutely, that's a huge area. Trying to design, say, new catalysts for more efficient industrial processes, like making fertilizer or generating hydrogen without needing expensive platinum. Understanding exactly how drug molecules bind to proteins. Modeling novel materials with exotic properties, like high-temperature superconductors or better battery materials. Quantum computers could provide data for these problems with an accuracy that's just impossible classically. Solving large-scale optimization problems is another classic target application domain. Think about optimizing delivery routes, financial portfolios, or network traffic.
And AI and machine learning.
Yeah, that's a really interesting intersection. Quantum could potentially offer advantages in analyzing massive data sets, identifying complex patterns, or helping make optimal choices in huge possibility spaces. There's also talk of using them to help design new AI tools or algorithms.
I also saw mention of using quantum to help train classical AI.
Yes, that's a fascinating idea gaining traction. Using a quantum computer, even an early one, to generate highly accurate, high-quality training data, particularly for scientific problems like chemistry or materials modeling. Then you feed that high-quality data into a classical AI model to train it.
So quantum generates the good data, classical AI learns from it.
Exactly. This generating quantum data for AI, or Gen Q AI, is seen as a potentially promising near-term application, maybe achievable with machines reaching, say, 50 to 100 logical qubits.
And what about uses beyond pure computation? You mentioned clocks and sensors.
Right. This is where the diversity of the underlying technology really shows another advantage, especially for approaches like neutral atoms or even trapped ions. The same core capabilities, precision control of quantum states, can be used to build incredibly precise atomic clocks or highly sensitive quantum sensors.
For navigation or medical imaging.
Things like that, yes. Or detecting underground resources. This offers potential early commercialization opportunities and valuable operational experience that can directly feed back into improving the computing efforts. Quantum technology is already making MRI machines more sensitive today, for example.
So usefulness isn't just one single thing, like beating a supercomputer on one specific problem. It's more nuanced.
It really is, and there's debate around the definition. Is usefulness defined strictly by achieving quantum advantage, clearly outperforming the best classical computers on an important real-world problem?
Or could it be something else?
Or is it enabling novel scientific discovery that wasn't possible before? Is it generating uniquely valuable data for AI models? Is it showing measurable performance increases when integrated into existing industrial simulation software, even if it's not a 1000x speedup yet?
Some people think we might see that kind of integrated usefulness soon.
Some experts we looked at believe we could see the first examples of industrial quantum advantage, perhaps integrated into existing software like simulation tools within the next 12 to 18 months. And that's before we have full fault-tolerant error correction. Remember, early classical computers were useful long before they were perfect. Others see maybe 2029 as a more likely inflection point for massive value creation in the right industries.
Okay, that brings us squarely to the timeline question. It's the one everyone asks. Where are we now, realistically? And when do these diverse machines become truly impactful?
Right now, as we said, we have physical machines with tens to maybe low hundreds of qubits. We're seeing demonstrations of early logical qubits, maybe up to around 28 currently reported. Progress is tangible, real hardware exists, but we're largely still in the phase of building the core technology and demonstrating its capabilities rather than solving massive real-world problems routinely.
The discussion around the timeline can feel a bit all over the place sometimes. Some high-profile people seem cautious, others sound incredibly optimistic.
Yeah, there was that initial comment from NVIDIA's Jensen Huang that seemed to suggest maybe 15, 20 years, which caused some ripples. His refined view and the consensus from many actually building these machines seems to be converging. Maybe 20 years is plausible for very useful, widespread platforms, but it's likely not 30 years away. And many players feel we're hitting an inflection point now.
Starting the steep part of the curve.
Exactly, starting that steep wall climb in capability. Some companies, like Rigetti and Pascual, predict significant value creation by the end of this decade, maybe around 2029 or 2030. PsiQuantum aims for their Brisbane site to be operational by late 2027, hoping for million-qubit machines just a handful of years after that. Microsoft is explicitly targeting 50 logical qubits this calendar year, then 100 logical qubits soon after.
And those numbers, 50 and 100 logical qubits, are seen as key thresholds.
They are often cited, yes. Around 50 logical qubits is where some think you start to see quantum computers potentially outperforming classical systems for certain specific problems. And around 100 logical qubits is often mentioned as a target for tackling meaningful scientific discovery applications in areas like chemistry or material science.
So it's really not like flipping a switch where quantum computers are suddenly useful one day. It's more gradual.
No, absolutely not. It's much better to think of it like turning up a volume knob, or maybe developing a new scientific instrument. Usefulness will increase steadily over time as the machines get bigger and better, as error correction improves, and, just as importantly, as we learn how to actually program and use them effectively for the right problems.
Like the early days of classical computers.
Exactly. Early electronic computers with vacuum tubes were bulky, unreliable, and the initial applications weren't always obvious. But they were the start of a revolution, and their capabilities grew incrementally.
And you mentioned the scaling rate needed is faster than historical trends like Moore's law.
Yes, that's a key point. To get to the required scale within the next decade or so, we can't just rely on doubling capabilities every couple of years. The industry needs and believes it can achieve much faster scaling, maybe factors of 10 increases in capability or quality metrics, enabled by new science, new engineering methods, and potentially leveraging those existing scaled-up industries like semiconductor manufacturing. Past performance is not necessarily indicative of future scaling rates here.
And from an industry perspective, companies thinking about using quantum, the advice seems to be to start engaging now.
That's the strong message from many building these systems, yes. Because once clear quantum advantage is demonstrated for commercially relevant problems, access to these machines and the expertise needed to use them will likely become much more competitive and expensive. So companies wanting to be ready are advised to start building partnerships, experimenting, and developing internal knowledge now.
Okay, this leads us nicely into the ecosystem. It sounds like the consensus view is that the future isn't quantum replacing classical computers, but rather a hybrid approach.
That's the strong consensus, absolutely. Across the board, everyone agrees the future is hybrid. You'll have quantum processors working intimately alongside classical computers, CPUs, GPUs, maybe other accelerators too.
GPU, CPU, GPU, all working together.
Exactly. Quantum is not replacing your conventional computing infrastructure. It's becoming a new, specialized component within it, integrated into larger classical workflows. Remember this scalpel versus hammer analogy. Quantum is the specialized tool.
What specific roles does classical computing play in this hybrid future that's not going away?
Not at all. Classical computers are absolutely essential. They handle the complex control systems that actually drive the quantum machines. They perform the heavy lifting for the error correction calculations based on measurements from the qubits. They process the outputs from the quantum computation. They're used for the design and simulation of the quantum systems themselves. And they act as the crucial input-output interface.
So there are engineering challenges just in connecting them efficiently.
Yes. Minimizing the communication latency between the classical control hardware and the quantum processor is a significant engineering challenge that needs to be solved for seamless integration.
And quantum's role in this partnership is?
To provide unique capabilities.
Yeah.
Generating that highly accurate data for scientific modeling, solving those specific, previously intractable parts of a larger computational problem, and maybe acting as a fundamentally new kind of instrument to explore and understand physical reality in ways classical computers simply cannot.
The synergy with AI seems particularly powerful in this hybrid context.
It really does. It looks like a very important two-way relationship is developing. As we mentioned, quantum could generate unique, high-quality training data for classical AI models, particularly in scientific domains, that Gen Q AI idea.
And AI helps quantum.
Yes. AI, in turn, is already being used to help design better quantum hardware, optimize control pulses, find better error correction strategies, and even develop programming tools and potentially new quantum algorithms. There's even some blue sky speculation about whether quantum principles could eventually lead to entirely new forms of artificial general intelligence, though that's much further out.
So even though all these companies are pursuing different, often competing technological approaches, there's still a lot of collaboration happening in the broader ecosystem.
Yes, that's a really notable aspect of the field right now. Despite being in a high-stakes competitive race to build the best hardware, there's also significant collaboration and ecosystem building.
Like partnerships.
Exactly. You see partnerships like NVIDIA working closely with many different quantum hardware companies to provide control systems and simulation tools. Microsoft is partnering with Atom Computing on the neutral atom front. AWS works with Rigetti and others through their Bracket Cloud platform. There are joint research labs, like NVIDIA's lab in Boston involving Quantinuum and others. And major industry events, like GTC's Quantum Day, bring everyone together. There seems to be a recognition that the overall challenge and potential reward are larger than any single company can tackle alone.
Maybe reframing the language we use is important for setting the right expectations. Thinking processor or instrument instead of computer.
I think that's vital, yes. Referring to them as quantum processors, QPUs, or quantum instruments rather than just quantum computers helps convey that they are specialized tools designed for a specific kind of complexity, distinct from the general purpose classical machines we're all used to. It helps focus the conversation on what quantum can uniquely enable rather than setting up an expectation that it will replace your PC.
It reminds me of the analogy that came up about how early GPUs needed a killer app, like computer games.
Right.
Something where the bar for absolute perfection wasn't impossibly high initially, but which drove volume and allowed the technology and economics to scale.
That's a really good analogy that several experts use. Finding those early application spaces, maybe in science or specialized modeling, where the technology can be deployed and provide value even with some imperfections, is crucial. That helps build the volume, fund the R&D, and drive the improvements needed for more demanding, fault-tolerant applications later on. It builds the necessary flywheel.
And these initial problems need to be things classical computers really struggle with.
They have to be, yes. The problems must be impossible, or at least highly impractical for classical computers alone to justify using this new complex technology. That's where some of the neutral atom companies see opportunities in clocks and sensors, potentially valuable early markets using the same core tech, helping to build that economic flywheel while the computing side matures.
Okay, looking ahead then, what are the experts predicting we might actually see happen in the next year or so across this diverse landscape? What should we keep an eye out for?
Well, some predictions included seeing quantum integrated into initial production applications that actually help customers, particularly maybe for optimizing AI model training or inference, perhaps with lower power requirements.
Tangible benefits.
Tangible, if maybe modest initially. Some predict prototypes of entirely new types of AI, potentially incorporating quantum ideas, will definitely gain significant practical learnings from the machines currently being deployed in cloud platforms and labs. One prediction was seeing the first tangible examples of AI agents actively working with quantum hardware to explore possibilities or design things in ways that would be too slow or require immense trial and error classically.
Hopefully less skepticism too.
Yeah, some hope to see less skepticism as more real-life value, even if specialized, starts to be demonstrated, maybe showing up in data centers. Others are predicting specific scientific breakthroughs, maybe 10 new significant discoveries enabled by quantum simulations across physics, chemistry, and biology. And continued progress on the hardware front. Further integration of core quantum functionality onto single chips.
And new algorithms.
Yes, critically, the emergence of novel quantum algorithms specifically designed for these near-term, maybe noisy machines. We'll also likely see more demonstrations of error correction working, showing that path towards fault tolerance is real, and maybe even physical construction starting on some of those large-scale quantum computing sites that have been announced.
That point about algorithms is key, isn't it? It's not just about making existing classical algorithms run faster on quantum hardware.
No, not at all. The real power comes from inventing entirely new algorithms that inherently leverage quantum phenomena like superposition and entanglement in ways classical algorithms simply cannot. That's a massive area for ongoing research and innovation, just as important as building the hardware itself.
So it really is a journey unfolding across multiple different paths simultaneously.
It absolutely is. It's complex, it's challenging, there are many different bets being placed on different technologies, but the whole industry seems to be scaling and accelerating now faster than ever before, driven by new science, clever engineering, and potentially by leveraging those huge existing industrial capabilities.
Okay, let's try and bring this fascinating deep dive together. We've navigated the incredibly diverse world of quantum computing today,
We really have.
exploring these distinct approaches from supercooled superconducting circuits and laser-manipulated trapped ions and neutral atoms to light-based photonic systems, electron spins in silicon, and even those exotic topological qubits. A whole zoo of possibilities.
And we've seen that despite these wildly different physical implementations, they all grapple with the same deep fundamental challenges. Maintaining those incredibly fragile quantum states' coherence. The inherent paradox of trying to isolate the system perfectly while also controlling it perfectly, the constant battle against errors requiring sophisticated correction schemes, and the immense engineering hurdle of scaling up to the large numbers of high-quality qubits needed.
And yet, remarkable progress is clearly being made across all these fronts, seemingly simultaneously. It's fueled by significant global investment and what feels like a rapidly accelerating pace of breakthroughs.
And I think the key takeaway for listeners is that these machines are not simply faster versions of the computers we use every day. They're fundamentally different instruments, almost a new category of device designed for tackling a specific kind of complexity inherent in the quantum world itself.
And they're expected to work alongside classical computers, right, in partnership.
Exactly, working in concert, acting as specialized processors or accelerators to solve specific types of problems that have, until now, remained stubbornly beyond our reach.
Their potential lies in unlocking completely new scientific discoveries, enabling breakthroughs in fields like materials science, chemistry, medicine, and potentially transforming aspects of optimization and even AI by providing novel data and computational capabilities.
And as these quantum processors become more capable and more accessible, perhaps the biggest challenge, but also the biggest opportunity for all of us scientists, engineers, businesses will be figuring out exactly how to best apply these unique capabilities to the problems that truly matter most.
So maybe a final thought for you, the listener. Think about the problems you encounter, whether it's in your own work or just in the broader world, that seem utterly intractable today. Problems that feel impossible to simulate or optimize with current computing power.
Could a quantum instrument, working together with classical computing and AI, perhaps offer a new angle, a new path towards a solution in the future? Keep exploring that possibility because this field is moving incredibly fast.